In the next chapter, we're going to be focusing a lot on polynomial and rational functions. In these first couple weeks, we're going to focus on polynomials, talk a lot about various different polynomial theorems, kind of some conclusions to draw from the process of dealing with more complex types of polynomials as we progress, and also focusing on zeros, how to find them, different techniques, different theorems, and how we can use them and apply them in order to do what we'd like when it comes to solving equations and stuff like that. So starting in this video, we're going to talk a lot about basic terminology and things like what we refer to as the end behavior, the intercepts, and how we can find those sorts of things. So a polynomial function, I mean, really we've already been talking about polynomial functions in the last few chapters as we talk about linear and quadratic functions, but a polynomial function is just a general term for an algebraic function which involves x, involves coefficients, adding, subtracting, multiplying, and, well, dividing, but not dividing by x. Now, when we consider what happens if we were dividing by x, that opens the door for what we're going to be doing in a couple weeks when we focus on rational functions, but I'm going to choose to do that at the very end after we've talked about as much as we can, as much as we have time for with polynomials at least. And so we often refer to polynomial by degree. And really the reason why degree is so important is the traits in the behavior of the polynomial there's a lot of patterns that you can determine based on simply the degree. Where the degree refers to the highest power of x that is within a polynomial function. So like in some of the examples from the packet, I've graphed a few of them here for you, starting with a linear function, moving to quadratic, cubic, and quartic. And each, with polynomial functions, sometimes each degree has a specific name to it. Like what we call a degree 1 polynomial, we often call linear, which we've talked quite a bit about, which has a particular slope and intercept, and, due to the fact that, well, there's no x squared, it's just x. And we often refer to it as degree 1 because the x is raised, I mean, it's just a singular x. It's not raised to any power, but you could imagine that it was raised to the first power. So if you're thinking, well, what is the highest power? 1, technically. Whereas we refer to as a quadratic function is also called a degree 2 polynomial because, we have an x squared within that function. And, we talked a lot about parabolas, where the vertex is going to be, all those sorts of properties, quadratic formula for solving those properties of quadratics. And moving into higher and higher degree, that's kind of our focus in this chapter because we've already really discussed linear and quadratics in detail. But say we move to, say, a cubic or a quartic function, which is just a word for a degree 3 or a degree 4 polynomial, what will happen is the graph becomes more complicated. There are more turns, which we'll kind of talk about what that means and how we determine all that. But basically, that's usually the purpose of examining the degree, is it will help us to determine more about the nature of that, because it really controls how it behaves. But anyway, some other terms we often refer to as the leading term as the term with the highest degree. So in like a lot of times in a textbook, it might have a generic polynomial written like this. And this can be a little confusing if you don't really know what it's representing. But basically, this is a way of saying, well, we're going to have some number times x to some power, where n is called the degree. So say it was like x to the 5th power, we would just say n is equal to 5. And this would be a sub 5 with the subscript notation, which would just represent a coefficient which is multiplying into x. So a 5 would just represent the coefficient on the 5th degree term, which could be any number, positive, negative, decimal, technically not 0, but sometimes coefficients other than the leading coefficient, which is just the one we refer to for the first one, the leading coefficient can be 0, but the other ones could be. Because if the leading coefficient was 0, that polynomial would not have that degree, if you see what I mean. But anyways, then, we would have terms of lesser degree as well. So let's say this was x to the 5th, xn minus 1, will 5 minus 1 be 4, then we might have the 4th degree term with its own coefficient. So that would, whoops, didn't mean to do that. We'd have a, say 3x to the 4th. But basically, this is just sort of a generic way of representing, well, this polynomial has degree n, and it could have terms of lesser degree in between. Like it could have x to the fourth, x to the third. That's kind of what the dot 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 here means, and there should be a plus here. Just if I'm because to not be sloppy with my notation. But we'd have the terms in between like x to the third, x squared, x, and then leading all the way up to our constant term. The term without an x is often referred to as the constant term, which, as we talked about with linear and quadratic functions, is always the y-intercept. So the same applies to any polynomial, because if we were to plug in 0 for x, remember 0 always gives us our y-intercept, all of these terms would go to 0 and be simply left with a 0. And the reason why the constant term is often phrased as a 0 is because it doesn't have an x on it, because a 1 is corresponded to degree 1 term. A 0 is corresponded to the degree 0 term, which is the term that doesn't have the x value on it. So anyways, like sometimes like in a quadratic, we refer to it as, well, ax squared plus bx plus c. We use different letters for each of them. But in a generic polynomial, we just use the a sub n in notation to represent all, because the higher and higher the degree, the more and more coefficients it could have. And so other things about polynomials, another generic property, something that you probably notice when looking at the graphs of these polynomials, is they're always what are called smooth and continuous functions. In calculus, you can really prove that based on, in calculus, you actually define what does it mean to be smooth and what does it mean to be continuous. But if we're kind of just eyeballing these graphs, notice that the curvature of them, they don't have any weird properties. Like they don't have any discontinuities. A discontinuity is like in a graph, if it were to say continue like this, and all of a sudden, I don't know, not continuous. It's literally what the word means, right? But if it jumps from one point to another, or if there's like a hole in the middle of your graph, anytime if you could, like, imagine taking your pencil along the curve and tracing along it. If at any point the curve has a break or a point where you can't trace it, that would be called discontinuity, like it would jump or have a hole or missing part of the graph. Well, it can be missing part of the graph and not be continuous, but we'd say it's continuous on whatever domain the function is defined upon. Anyways, and also, what does smooth mean? Smooth means there's a few things that are what we classify as not smooth with curves. Something called a break or a jump. And so I kind of was talking about what that meant, or holes. A corner or a cusp is something else that is problematic. Again, these are things that are important in calculus, and they can cause a function to have no derivative at a particular spot. But a corner, is exactly what it sounds like, would be a sharp point. Like with the absolute value function, it has a corner. Polynomials will never have that sharp corner. Or a cusp would be sort of similar. It would look something like this, where it kind of goes up to a sharp point and kind of falls back downward. But anyways, there's all sorts of graphical behavior that could happen. Polynomials are never going to have sharp corners or cusps, and they're never going to have breaks or holes. So they're always going to have that smooth, continuous shape. And so kind of the next goal is in a lot of these functions to analyze those sorts of properties. Like, what about their degree? How does that affect the number of turns, intercepts, and what we call the end behavior of that function? I'll do that in the next video because this one's getting a little bit long. But in that video, we will look at a lot of these functions and try to figure out what's going on just based on the graphs, and see if we can make some generalizations that make sense about those functions themselves.